partner at SARAD Enterprise Partners. We are the sponsor, along with Racing, for this Nozik lecture series. We began being a sponsor a year ago, and so I'm happy today to kick things off by saying a few words about Art Nozik. So creating a named lecture series is not a common thing, but it happens from time to time when someone makes significant contributions to science and technology and important institutions like the University of Colorado and the National Renewable Energy Lab. I met Art in the mid-2000s. In fact, I think I took my first graduate course in chemistry from Art, and then was lucky enough to be managing director of CRISP, supporting Art as the scientific director. This was the Center for Revolutionary Solar Photoconversion. It was joint between CU, CSU, Mines, NREL, and a number of industry companies. I then interfaced with Art many times, often after I left CU Boulder, often asking him for insight, scientific insight about this idea or that idea that my firm was investing in or researching. And the last couple of years, I've invited him to our annual Hydrogen Mountain Retreat and just enjoy every opportunity I get to interface with Art. So I'm going to say a few words about Art's background in three buckets. The first is just his contributions. Second, his roles. And third, a few awards out of many that he's received. So when you think about the Nozik lecture series, of course, photochemistry, photophysics is at the core of that, which you'll see represented in the thread of today's lecture. His research contributions span a number of fields relating to this, including size quantization of hot carrier effects in semiconductor quantum dots, including my favorite area, multiple exciton generation with a single photon. Advanced approaches for greatly enhanced solar photo conversion efficiencies for production of electricity and solar fuels, photogenerator carrier relaxation dynamics in various semiconductor structures, photoelectrochemistry of semiconductor molecule interfaces, photoelectrical energy conversion and photocatalysis, optical, magnetic, and electrical properties of solids, and Mossbauer spectroscopy. You take all of that and then think about the many roles he's held. He kicked off his career at Cornell, picking up his undergraduate in chemical engineering, and then at Yale earned his PhD. He then worked in industry, including at Allied Chemical, which is today part of Honeywell. And then in 1978, he joined NREL. Now, who here knows what NREL was called in 1978? Siri. That's right, Siri. He then led various organizations while at NREL, including CRISP. He was also associate director at the Los Alamos NREL Joint Institute for Advanced Solar Photophysics. He was senior editor of the Journal of Physical Chemistry for 12 years and served on many editorial boards for many journals. He's published over 240 papers, each factor over 100, 52,000 citations, and written or edited 6 books, 11 patents, delivered nearly 400 invited talks, et cetera, et cetera. Today, he's a senior research fellow emeritus at NREL. He's a fellow emeritus at Racing, research professor emeritus here at CU Boulder, and a fellow member of many scientific societies around the world. And then finally, just a few of the awards that Art has received, in addition to this named lecture series. Two of my favorite, in 2008, Art received the ENI Award from the President of Italy. And that, as some of you may know, is considered the Nobel Prize of Energy. And then just last year, he was inducted into the American Academy of Arts and Sciences. The induction ceremony held at Harvard University. And when Art signed the book as an inductee, he noticed other names in that list of members, including Benjamin Franklin, George Washington, Albert Einstein, and many others. So I'm very proud today that my firm S&P is able to sponsor this and say a few words about Art. And I'm going to turn this over to Seth to introduce our lecture today.
Well, thank you, Paul.
And let me start by thanking you and Sarah for sponsoring, co-sponsoring this lecture with us. I'll just say a few words about Richard because I don't want to take too much of his time. So it's really a personal and professional pleasure to introduce Richard. Richard was the Cavendish Professor of Physics at Cambridge, and during his tenure in that position, I think it is fair to say that he pioneered semiconductor polymers, light-emitting diodes, and solar cells. He also established Cambridge, not just the university, but the city, as a global hub for plastic electronics. And in doing so, among other things, he co-founded several companies, including Cambridge Display Technologies and Plastic Logic. He's mentored multiple generations of leaders, and one of the things we were just chatting about is the number of people who passed through Cambridge, and in particular his group, on their way to being immensely successful contributors to the field. He served as an advisor to not only the UK government, but multiple governments around the world, both science and commercialization and translating academic science to actually products that actually touch people's lives. He has been an ambassador for UK science, fostering global collaborations. We're fortunate to be part of a joint program right now involving folks at Cambridge, Oxford, and here. And he's continued to evolve, as you'll see today from his talk. Richard is received many awards, and I'll just mention a few. In 2003, he was knighted for his services to physics. He's won the King Faisal Prize. He's a fellow of the Royal Society, won the Millennium Technology Prize with Donald Bradley and Paul Burroughs, the Cavendish Prize, and the Isaac Medal. So with that, I'll turn the floor over to Richard so that he can tell us about what he's been thinking about lately, and then Dan, I think we can change the screen. I guess I'll stop sharing.
No, you could say.
I'm sorry?
You did it.
Oh, you already did it. Okay, great. Richard, the floor is yours. Welcome to Boulder.
Paul, Seth, thank you very much. It's wonderful to be here. Thank you both for making that possible. And Art, it's a real honor for me to be giving this lecture that's in your name. I think for many of us who feel very passionately that we need to make the world work, and solar is such an important part of that, what we've wanted always is to see scientific leadership and inspiration. And it's been a hard sell to pick large area semiconductors up to be areas where there is really groundbreaking science to be done. And we need inspiration, which you really have given us, the concept of multiple exton generation, splitting photons, exploring what might be possible to make solar cells really wonderful. I think I forgot to turn this on. Apologies for that. You have done that, and that's been so important to many generations of us as we've looked to see where we can find new science and turn it into applicable science that makes a difference on a large scale. So thank you for that. So my talk, I hope the title isn't too long-winded. The theme that runs right the way through is that if you want a semiconductor to be really useful, and it's anything to do with light, is it better to be bright? It's sort of obvious if you're trying to make a light-emitting diode. It turns out to be equally important if you want to make a really good solar cell. And the business of trying to get molecular semiconductors to be very luminescent in the solid state where we have electrodes on them has been a slow and interesting process. And I want to give you some insights of things that we've done from some time back and things we've done more recently. So my introduction to the world of organic semiconductors was in the early 1980s when it was just becoming possible to find thin films of molecular semiconductors that were clean enough and capable of being made flat enough to think making semiconductor devices. We had an important discovery for us. Back in 1989, we published a paper in 1990, where we made this very simple structure of a substrate. Get the pointer onto. There's a pointer. It's terribly simple. We had a glass substrate, a semi-transparent indium tin oxide bottom electrode. We painted down a layer of this polymer, polyparaffiniline binding. For those who like the chemistry, you can see that it's conjugated. So we've got alternating double and single bonds if you want to draw the structure like that. But that's telling us that there are pi electrons and pi star unoccupied states, and the optical transitions between the two use a material that emits green light. So on top of that, we put a top electrode. The one that works best is actually calcium, and put some bolts across it. Remarkably, it produced light. I have to say, back in 1989, it wasn't very much light. I hope you can see this unimpressive little bar of light, but it was enough to know it was working. The nice thing about something which glows, I just recommend this if you're trying to make an impact with your research, is that you can actually call people from down the hallway, and they politely say that they're very impressed, but they definitely know they've seen something. So that was good. And it turned out that this was one of the very early demonstrations that we could use molecules or strings of molecules as polymers to get electrical energy into light. We did form a company, Cavendish Display Technology. We found a patent, which was a good thing to do, as it turned out. And it was a starting point. The fact that that has gone on to produce, I mean, obviously many, many other people played very big roles in all of this. But back in the day, these were very, very crude devices that didn't last very long and weren't very bright. But years later, everybody in this room possesses, several million organic light-emitting diodes in your smartphones. Every single smartphone is now an organic LED display. We've displaced the crystal displays because they're brighter, more power efficient, and take less space. They're astonishingly good. There are TVs, and the one I've shown there is one that's particularly interesting to us. It's ECL, which is a very large manufacturer of electronics in China, and that they are in the process of building a $4 billion manufacturing plant for our solution processed LEDs, where they are printing the separate red, green, and blue subpixels to produce large TV screens. So there was a sort of trajectory through what we developed at Cavendish Display Technology to what is now happening in China. So a bit more about how the devices work. And I'm going to show you a device which has been, some purpose has been to show you this video. So what we've got is a transistor. And the transistor comprises 3 electrodes. So we have the same glass substrate. We have 2 gold bars, or thin evaporated gold, 20 microns apart. So that's, you can see it. And you can see on the right, a black and gray differentiation. The electrodes are actually interdigitated, so we've got lots of channel for the transistor. So we put a polymer semiconductor, the green layer there, its structure is down the bottom, and then an insulator, which is polymethyl methacrylate. It's easy to paint that down, and then a semi-transparent evaporated gold layer on top. And what it's done with the transistor is to establish an electric field across the dielectric, in which case we must have charges either side. That's Gauss's theorem. Charges in the metal layer, of course, are trivial. You can charge a metal surface. Charges in the semiconductor, and what would have had to have happened is that holes, electrons or holes were introduced through the electrodes to build up this surface charge layer. Now, usually when you look at a transistor, you can think of it as a p-type device, in which case the accumulation of charges, of positive charges of holes, or an n-type, where we've swapped the electric field across the dielectric to put electrons in. You can occasionally make an antipolar transistor where, if the voltage between the source and the drain is huge, and we set the gate voltage somewhere in the middle, the electric field will actually swap across the channels. So we've got electrons to the left, holes to the right, and there's a great big electric field because we've got a big voltage minus V between two. So the electrons will be heading from left to right, the holes from right to left. Where we meet, we get some light, I hope. So what you're going to see is controlling the gate voltage to determine where in the channel electrons big holes. And here is the line of light creeping out from under one electrode. And you can see it running across the channel. That's a 20 micron gap between the source and drain, doing a fringe electric fields. It's nice to know that Maxwell's equations work. And there you can see that when electrons meet holes, they produce light. You can move electrons or holes or holes through this material. It's a semiconductor and it's bright. So that is my sort of single slide of a working device, because it sort of encapsulates everything in one slide. It's actually quite an efficient device, but not necessarily useful. So I'm going to dive a little bit into spin, because that's going to matter quite a lot through this talk, because the devil behind all the challenges of making light-emitting diodes with organics, and actually now getting really good efficiency from organic solar cells, is the problem that electrons and holes are very strongly bound in molecular semiconductors. Just the electrostatic attraction to an electron and hole is stronger in any of our organics than it is in silicon or gallium arsenide, because the background dielectric constant is much smaller. So if you absorb a photon in some silicon at room temperature, we expect to have a free electron and a free hole. They will diffuse away, and you could collect them on a solar cell. But if you absorb a photon in a molecular semiconductor, you'll generally get a localized excited state, which you can view as a bound electron hole pair. And its size is very important. So here are some calculations for this molecule, something called pentacene. It's 5 fused rings of benzene. When it crystallizes, it's possible to calculate what the wave functions look like. So we have a hole on the middle molecule, and here is where the electron lies. It's not just on one molecule, it's spread over the nearest neighbor and to a bit to the next nearest neighbors. It's we call it an exciton, an excited molecular state, but it's much, much tighter, much more confined than you would see in an inorganic. And that's just down to the low dielectric constant. So there it is in the spin signet state, where we've excited an electron from the filled valence band level up to an unoccupied conduction band state from pi to pi star. And if we photo-excite, the electron hole will remain in the signet state. And the signet state, actually, the electron holes stay away from one another. But in the excited state, I could swing the electron spin round to have them both pointing in the same direction. That would be a triplet. And the way that the antisymmetrization of the spatial wave function then works is that the two electrons in the excitation keep well away from one another. They're never at the same place, but therefore they can condense to a much smaller object, a very, very different size, just down onto one molecule. And in doing so, it becomes much lower energy. It drops to about half the energy of the single exciton. So the triplet is much lower energy singlet. The triplet is not really supposed to luminesce because it's spin forbidden. You have to change the overall spin, go from the S equals 1 excited state back to the ground state. So if it does emit, it emits very slowly, that means phosphorescence. And that's sort of well known as a general phenomenon. It becomes a very big deal in a light-emitting diode. The problem is that when I photo-excite, I get a nice luminescence yield because the two electrons are in a singlet state in the Bowley's level. They remain in the singlet state in the excited state, and they drop back again. Everything's fine. But when I bring an electron and hole together from either side of the diode, they don't know what their relative spins are. So when they collide, they do so statistically. And the clue's in the name. There are 3 times as many triplets as there are singlets. So 3/4 of the electron hole collisions produce triplets, and they don't emit. So if that were the case, we wouldn't have smartphones made of OLEDs because they wouldn't be efficient enough. So we have to do something to get the energy, get light out of triplets. What you have in your smartphone are 2 different technologies to do that. For the red and the green pixels, you have some iridium, or if it's a newer phone, some platinum in it. It's an organometallic complex that is the light emitter. And the heavy element has strong spin-orbital coupling. It mixes up what is singlet and what is triplet, so you get fast enough emission so that light comes out as phosphorescence as a lifetime of about a microsecond. That works quite well. It's not been engineered to work blue yet, not quite. And in blue, something more exotic happens. It's still just a hydrocarbon system, so triplet excitons, they don't emit, and they hang around for quite a lot of time. And what is done is to engineer that we bring electron and hole together. I can take you to the top left-hand corner of the slide. Electron and hole combine to form an excited state. This exciton, of course, will make singlets, which will give rapid luminescence. The 3/4 that make triplets, you can build up a high concentration of them to the point where the decay channel for triplets is that 2 triplets fuse if they're an overall spin state to make a singlet. So we need 2 triplets, but we make 1 singlet because there is enough energy to do that. So we have a little sort of fusion converter. There are some molecular designs to arrange that happens quite efficiently. And then that makes some singlets, and then we get some emission that comes out. It's very easy to know that's happening because the kinetics for this for the fusion process are actually quite slow. They run out towards many microseconds. It's very easy to time resolve. The plot on the right just shows what happens when you switch the diode off. There's a sharp drop as you've lost the singlets, and then a slow decay following a bimolecular kinetic as the fusion of triplets runs its course, and you see emission coming out of it. It's not perfect. The efficiency of the blue pixel in OLED is pretty rubbish, and it would be lovely to get a better solution to it. So that's today's technology. So the 2 things that I'm going to try and carry on with are, 1, we want things to be bright, very luminescent, and 2, we need to manage the triplets. So I'm going to turn briefly to the reverse process, the solar cell. The existence proof that organics are the best materials to make solar cells out of is photosynthesis. The key step in light absorbed by green plants or whatever color bacteria is that the energy from the photon responding as excitons to the reaction center, which is basically a little diode that separates electron from hole. It's the electron which is then used to do reductive chemistry to turn carbon dioxide into sugars or whatever. There it is. It's the most abundant semiconductor device on the planet, and it works down well. Obviously, it's interesting to try to do something similar with our synthetic materials. The challenge is that whereas in nature there is this very exquisite, I have to be careful using that word, it's a beautiful design where we have many molecules that absorb photons. Energy is then funneled down to the reaction center, and away from that, we then generate separated charges. That's the solar cell bit, which are then harnessed to do chemistry. So, of course, we're not nearly as good as nature at making devices, but the sort of proposition is that if we can use plastics, solution process molecules, whatever, we can make solar cells with less material, and lots and lots of images such as this, roll-to-roll printing of stuff that probably is a solar cell. There's some lovely examples of that. They haven't commercialized yet. How do they work? Well, there's a very, very important paper from Ching Tang, some images of that from his paper in 1986. Ching was at Kodak Labs in Rochester at that time. He also produced the key paper for organic LEDs shortly afterwards. And the key was to have two semiconductors, which you can just about make out a little cartoon top left, one on top of the other, with different semiconductors with different electron affinities. So the deal is that if we have an offset of the energy levels, this binding that keeps electron held together in the excited state can be overcome by the electron moving from the one with up to the higher LUMO level to the one with a lower LUMO level, a charge transfer process, where the driving force is that the lowering of energy as we move the electron from the donor to the acceptor. And he showed very beautifully that will work, but only when light is absorbed right at the interface, because the exciton has to be at the interface. So that was very, very influential. What has made things possible to get high efficiencies with organics is to turn that abrupt interface layer by layer into an interface everywhere by forming a bicontinuous network interdigitation of electron donor and electron acceptor. There's a cartoon of that on the right. And there are many ways of doing that. The ones that we use with the organics are extraordinarily simple. We mix together a donor material and acceptor material with a solvent, and if everything works magically well, it self-organizes to form this nanostructure where the key is that light's absorbed close enough to the heterojunction that you'll always get the charges generated. And essentially, you can get close to 100% charge collection with that structure. So that happened in 1995, and since then there's been a huge effort to make organic solar cells work. This is an early, just where I say a bit more about that process of charge transfer. On the left, we have the valence and conduction levels for a donor, it's a polymer in red, and then offset levels for an acceptor, which happens to be a derivative of fullerene. And what we see is, in this case, the electron, the excited electron, following absorption of the photon on the polymer, drops to a lower energy as it moves to fullerene. That's how we drive the charge separation. Over many years, the material sets have changed. There's been wonderful work, very significantly in China these days, and there are several reports, pretty reliable reports, of a 20% power conversion efficiency for this sort of organic solar cell. It's not as good as perovskites, it's not as good as silicon, but it's come a long way and it keeps on getting better. And it's the closest we've got to nature as a converter of photons into electrons. So what do we have to do to make them better? Well, the answer is that we have to make the material brighter. The ideal solar cell, if you choose not to wire it up, should look particularly fluorescent. Photons absorbed produce electrons and holes, which can't escape because we haven't turned the device on, so they should recombine, produce photons out. We don't expect to see that because we don't see that with silicon. And first of all, it's not very luminescent, and secondly, it's flat. So we haven't been sort of tuned to think about a solar material as being luminescent, but we definitely see that with perovskites. And we starting to see that with the organics. But I think the major challenge we've now got is that the same triplet exciton that we've had to engineer for light emission is also a significant non-radiative decay channel in the solar cell too. It's exactly the same slide that you saw previously. Take a snapshot of what you've got when you photo-excited. You have electrons and holes that are separated across the heterojunction. They could have been injected from the two electrodes when LED. Electrons and holes, through the dynamic equilibrium, they will recombine and then reseparate. That's how solar cells should work. But the recombination can form triplets, and it's something we've studied over the years. They really do form, even in these 20% efficient cells. And finding ways to get rid of those triplets is going to be very important. So that's a sort of quick run through about 3 decades of efforts with the organics. I'm going to run through things that have been going on in my group in the last few years, where we've been doing things that have sort of changed some of the story. One of the some work we published earlier this year is to make the material chiral. And chirality is a topic of huge interest. I had a wonderful day yesterday at NREL, and chirality in perovskites is turning out to be a really important way of exploring quite surprising quantum phenomena. The materials we've looked at are, of course, molecular. This is a wonderful collaboration with a group of Bert Meyer at the Technical University of Eindhoven. And we're using planar molecules. They look like, well, they're not like little pieces, but they could be like little bits of graphene, except they've got some nitrogens in it, but don't worry about that. They're flat. But if you put some side chains on, they become quite soluble. And you can put chiral side chains on, which will give a handedness. You can make them S or R to give a preferred handedness. And if everything works wonderfully well, when you crystallize it, the planar semiconductor bits stack to form a column. The side loops hit the stack in the right twist. So you can end up with right-handed or left-handed screw threads. And we know the full crystal structure. Student were to did a brilliant job solving this structure. And there's a stack of 6 of these molecules gives a rotation of 120 degrees. It really is like quite a tight screw thread structure. And that's enough to impart chirality into the, not just the structure, but into the electronic structure. I will dive down into a bit of electronic structure. Our colleague Tommy Monstrat runs a working group solving electronic structure for very large unit cells. So he was able to sort out how the electron hole energy states disperse with momentums. As for those who like band structures, here is one. But what we are able to see is that the conduction and valence band states can either that they are circularly polarized electron or hole states. They can be right-handed or left-handed. At high symmetry points in the Riemann zone, they're standing waves, but as we move away from the high symmetry point, they disperse differently. We have one electron state that has the same handedness as the actual structure, which disperses more quickly, but the other handedness that goes against the handedness of the structure. So we have this separation of bands, each of which has now got orbital angular momentum. It's now, we've mixed in an L number in addition to, well, obviously going to be a spin number when we put an electron in. What that does is to give very strong circular polarization of the luminescence. The 2 plots there with the material which is green, quite ignore the spectrum, show right or left handed circular polarization for the S structure for this material. So that's in a sense fun and nice to be able to do. In principle, secular polarization improves the efficiency of OLED displays because there's quite often a secular polarizer to take out back reflections. So there's an interest in doing that per se. But one of these we were able to do was to make LEDs with the structure. There's some details on how we can make thin films, which I'll pass by. But with the OLEDs, we run through what an ordinary structure should do and what we would expect. We have a luminescence efficiency of about 50% or 56%. If you run through how much light we'd expect to get, this is a system where we should lose 3/4 to photons, just get a quarter of bright singlets. And only about a quarter of those will exit in the forward direction. The rest get trapped in plane or head downwards. So the standard models, we would expect to get an electroluminescence quantum yield of about 3.5%. We measure 2.9% for a material which is not chiral. It's one of the structures I showed you earlier. Really surprisingly, the chiral structure is 4 times brighter. The external efficiency is rather funny. It's as though there are no triplets. It's a surprise. We put 2 options for how this might be: a boring explanation, which we don't think is right, and a more exotic explanation, which is that it is to do with the chirality. We're now using states that have got L as well as S, so the total quantum number is J, and we can think of transitions that change the S quantum number, preserve J. It may be that that is what's giving us the factor of we're getting the missing 3/4 of the excitons are emitting quite efficiently. It's a big surprise. We don't really understand why that's happening. So that's a piece of work which I think it sits in parallel to, but rather different to, the beautiful work here on chiral 2D perovskites. So the second example that I want to run you through is changing the spin on the molecule that we use as a semiconductor. We're going to work with radicals. Now, radicals are usually the point at which you think that you're going to age too quickly, as radicals are bad for you. And many radicals can be highly reactive. But there are perfectly stable structures where we have only one electron in what ought to be a doubly occupied or unoccupied orbital, where the redox potentials are perfectly in a perfectly sensible zone, the same sort of range that we do standard organic semiconductor electronics. And a motif that has proved pretty useful is this one here. The acronym I'm going to use is TTM. We have 3 benzene rings, they have chlorines on, which are linked onto a single carbon. And because there are only 3 bonds, there is a leftover electron, which isn't able to sort of pair up with another electron to make a double bond, because they're already paired up within the benzene rings. For this structure, where we have an odd number of carbons, the only option is that we have a spin that is actually quite confined to this central carbon. So it's a sort of pz orbital, and it's has quite interesting symmetry protection. It is a non-bonding orbital, but in a very, very profound way. There is quite a literature on these, and until recently, these were rather dull, literally not very bright. But in various ways, it's proved possible to make them very bright. There's important work that came originally from a group at Barcelona, where if you do some more chemistry, here's a molecule where we've got a carbazole linked on to the TTM. The optical transition that makes it bright is one that moves an electron from the lone pair on the nitrogen to pair up with the electron on this radical carbon. And that's an allowed transition. And it absorbs moderately well. It emits very, very efficiently. And the spectrum quoted on the right, this particular molecule is just beyond red. It's quite far towards the near infrared. So in terms of energy levels, what we have is the HOMO level, the doubly occupied level, which donates an electron, is sitting on the carbazole. When we absorb a photon, we take one of those electrons and transfer it onto the radical or that excited state, and then it can emit down again. And it's bright. We have very high luminescence yields. They're heading towards 100% in many of the structures that we're now looking at. And there's no triplet. The equivalent of what will be a triplet is actually 3 spins. So we have an S equals 3 halves. And the lowest energy way of doing that is to take one of these electrons and push it up to the LUMO level. And you can easily see that's a higher energy excitation than the doublet. So we re-engineered the structure so that whereas we're always taught there's the singlet and there's a lower line triplet which is dark, we've now got the doublet which is bright and the quartet, which would be dark, is higher. So we solved the dark lower line state problem. We have made very efficient LEDs and red, clear infrared with this. It's a very simple trick of just rearranging, just changing the occupancies of the levels, flips the relative energy orderings. We're quite puzzled that, and this is a smaller side, as to why these things are so luminescent. We had a paper last year where we explored that. I mean, please don't glaze over and let me put you off too much. But for those who like chemistry, these two structures are almost the same. One of them has a luminescence yield of 14% solution, the other 92%. The only thing that has changed is how we have connected the carbazole onto this phenol on the TTM. The one that is bright, we have a meta-linking from the benzene phenol onto the carbazole, so that the optical transition is from non-bonding nitrogen to the non-bonding carbon, whereas where we've rearranged where we connect it, we've now got, it turns out the most accessible donor state is now fully conjugated across 3 benzene rings, and we've now coupled in to the the 2 benzene rings on the carbazole. The difference it makes is that the transition where we get high luminescence yield is from non-bonding to non-bonding. That is vibrationally decoupled, whereas whenever we use a pi or a pi star state, its energy depends on the bond order. If we change what is long and what is short, the pi and pi star levels go up and down. So when you do an optical transition, you can involve phonons, and those phonons can quench the luminescence. We can design in to get rid of the quenching and get really efficient luminescence, far, far redder than is usually possible for electron systems. That's inside. So the final bits, which have really been happening in the last 2 years, which was a long way from what we thought we were going to be doing, is what happens if we couple spins together. So we can have one of our molecules here and another one here, and we can control how much contact there is. We can physically bring them together, or we can put in a covalent coupling between the 2 radicals and control precisely what the interaction is. So that's coupled radicals. Now, for those who come from the inorganic world and know about cuprate superconductors, you'll be aware that there are many, many transition metal materials, transition metal oxides, where if you just look at the band filling, they ought to be metals, but they're actually antiferromagnetic insulators. So something like nickel oxide or the the cuprate superconductor undoped. And the grounds, when you look at them at room temperature, they're antiparamagnetic insulators. They're a sort of set of states where there is a net spin. The spin is associated with the diol. If you could pull the transition ions close enough together, the interaction between them will become strong enough that we would turn them into metals, as we have with metallic copper or metallic nickel. But when they're far apart, they're insulators. And that's exactly it's an accurate analogy for what we're able to do with our molecular systems, as I'll explain. So these tend to be antiparamagnetic. The process, the sort of process that sets it that way is what happens if we move an electron from one site to an adjacent site. So we go from, which then gives us a positive charge where we've moved from one site, and a negative charge where we've doubly occupied the adjacent site. That excitation has costs some energy. It costs energy to, it's the Coulomb repulsion between the two electrons that are sitting on one site. In physics jargon, that's called the Hubbard U, on-site Coulomb repulsion. And it's quite consequential. What we have sort of realized is that this process of moving charge from one site to the other, so we go from spin up, spin down to nothing at all, and spin up, spin down on one site, is optically active. It's dipole coupled, so it's actually bright. And so going back to the principle that we always want things to emit light, and so that has been a surprise. So if we could do that, my description of the excitation being one that naturally separates charges, could we make a decent, could we make such a material be an intrinsic photoconductor without needing the heterojunction? It's something we find ourselves exploring. People work on a GBP1B, we published it recently. So the molecule happens to have Hanel groups around the edge, which and if we bring them close enough together, the Hanel groups provide some intermolecular contact. And what we hope we do is when we absorb photons, we will see both electrons and holes appear magically, because that's the lowest lying excited state. So what we can do is to look for a color change. And what you see on the left is what happens if we oxidize or reduce electrochemically. And what you see is the absorption at about 450 nanometers is quenched as we oxidize or reduce. If we reduce, we see an absorption band at 600 nanometers. If we oxidize, we see at 750 nanometers. That's the sort of sanity check that we know what charges look like. So now we're going to photoexcite, absorb photons. And what we start off with is an absorption associated with the initial excitons. And then as time goes by, we see the appearance of the anion and the cation. You see an optical signature. We've got both charges intrinsically photogenerated. And if that were to work, we ought to be able to extract charges in a solar cell. I will briefly show you the sort of placebo or comparison device where we've got a standard heterojunction, very much like the Ching-Tang device, between a donor, which is rubrine, and an acceptor, which is C60. And if we absorb light in that structure, we've got electrodes top and bottom, it's only light absorbed very close to that heterojunction between the donor and acceptor that generates charges. So we get about a 10% charge collection efficiency for that structure. But if we now replace the rubrine with our radical system, it's now 100% radical, we essentially get, we've got 100% charge collection. We have generated electrons and holes. I have to say we need a bit of voltage to extract them, about 10 volts to get them all out. But it's an intrinsic photoconductor with no heterojunction, just playing on this simple business of moving an electron from one site, from its non-bonding orbital, leaving behind a positive charge, onto the adjacent site to create a negative charge. And they're far enough apart that we can pull them out. So we've got a very good photoconductive device. Probably not useful yet, but it was a pleasant surprise. So that, I hope, gives you I hope I've convinced you that we can get that charge separation process. It plays in a very strange way when we start designed chemical couplings. I really must mention my chemistry colleague, Bronstein, particularly his postdoc Petrimoto, who came up with a whole series of diradicals. So we've got the same motif of spin surrounded by benzene rings, but now two of them with a coupling unit where we can control how much interaction there is between the two spins. What we see in the luminescence are two bands, one at about 640, so that's deep red, and one at 700 nanometers, which is out in the infrared. And you might think that they have the same origin, that one was a vibronic overtoning of the other. And by the way, the lens is bright, so blue laser light coming in and red luminescence coming out very, very liberally, and they're easy to see. But remarkably, it isn't what's going on. What we're actually getting are two different emissions from whether or not the two spins were parallel to start with or anti-parallel. So the key experiment, which is courtesy of Alexei Chepelyansky in Paris at Orsay, he has a dilution fridge, and we don't have to pay the electricity bill for running it. So we're down at 1/4 of a Kelvin, looking at the luminescence. Down at 1/4 of a Kelvin, the two electrons are antiparamagnetic. We've got an antiparamagnetic exchange. And the luminescence comes out at 700 nanometers. If I put a magnetic field on, this is overkill, it was 7 Tesla, the superconducting magnet there as well. The magnetic field will swing the two spins to be parallel, and we force it to be a triplet. And the colors change. We go from 700 nanometers to 640 just by applying a magnetic field. So the magnetic field energy is about 1 Kelvin. The color shift is about 250 millielectron volts, that's 3000 Kelvin. But the gating of what excited state we can make is just by the initial spin configuration, just flipping it, determines whether or not we can get this charge transfer process, which is what we're getting with our photoconductor. And if we do, we get the redshift of emission. And that's really good because we've now got a very differentiated triplet and singlet levels. And we have both triplet and singlet ground states. And it's a really interesting quantum object. Briefly, and I hope I don't cause howls of indignation, there are quite direct comparisons with the nitrogen vacancy center in Dunn, which is a sort of favored spin-optical quantum bit. And the key with the nitrogen vacancy center is the ground state triplet and a singlet, which is not seen very much, but you can set the spins of the sublevels of the triplet by optical excitation or microwave control, and it's possible to use it as an optically set, an optically read qubit. And we're starting to do similar things with our diradical. So the most recent work, which is on archive, lots of referees who are not very happy with it. There we go. Slightly different chemistry. The coupling group is a phenyl or a pyridyl, and it matters how the pyridyl nitrogen is selected. And these again are very bright. Here we're applying magnetic fields, but we're at room temperature, and we're not applying Tesla, we're applying millitesla. And remarkably, at about sort of 30 times the Earth's magnetic field, which is 2 millitesla, we can get up to a 10% suppression of the luminescence. Well, it's actually the triplet of emission of 630 nanometers. There's a huge magnetoluminescence and a tiny magnetic field, which is absolutely bizarre, but quite useful. We can tell what's happening because it's possible to do electron spin resonance with that at zero field, at room temperature. This is work done with Sam Bayliss at the University of Glasgow, who does wonderful detected magnetic resonance measurements. Essentially, we can drive, we can change the spin populations between the M0 level of the triplet, between that and the plus and minus triplet sublevels. The frequency that couples the two is actually quite low. It's as low as 50 megahertz. And then if you apply a magnetic field, the Zeeman energy will then further split the T0 and the T plus T minuses. And as we apply a magnetic field, plus and minus, the resonant frequency follows the trajectory of these white lines. So that's just to show you that we know what is changing with these low fields. So why is that happening? Well, that's a really interesting question. The sanity check is, well, first of all, why do such small magnetic fields make a difference? The answer is that compared with the NV center, where the resonance frequency at zero magnetic field is a couple of gigahertz, we're down at 50 megahertz. And the reason is two spins are far apart. Usually, triplets, the two spins are absolutely piled on top of one another. So the dipole-dipole interaction between them is large, hence the gigahertz. Here, we've deliberately spaced them out. Well, we can deliberately do it, that's how we have to make it. The spins are a nanometer apart. And if you look at that splitting in the ground with low magnetic fields, at 1 nanometer separation, it should be 50 megahertz. So if we want to get some comfort from that, there is some beautiful work, which is summarized from little bits out of a Scientific American article from Peter Hoare in Oxford. And he and colleagues have been trying to understand how certain songbirds, the European robin, are able to navigate using the Earth's magnetic field, in spite of the fact they've got nothing apparently magnetic in them. And the surprising story is the back of the eye, there are molecules that are not there for vision. They're there to generate pairs of spins. There's some photoexcitation, there's absorption of a molecule which is helpfully called a cryptochrome. That generates a radical pair, a positive radical, negative radical. And it is proposed that those two radicals, those two spins, how they set themselves up as singlets or triplets, then determines how they do chemistry, and that is then coupled through to give a response in the bird's brain. But that must happen at these very low fields. And what is happening is that we're switching the overall spin state from being set by the dipole-dipole interaction between the two spins with no field to a new set of eigenfunctions set by the Zeeman energy of the magnetic field. And that's happening about 2 millitesla. So I'll finish with a little video, which was made last month, a month ago. It's Ritapano, who's done most of this work. We have a brilliant master's student who's joined us recently, Q Young. So what you see here is a laptop screen with the luminescence signal as a function of time. On the right, you can see the sample, which is okay. I've got some stuff on my screen, so I'll explain it over. You can see something that is a purplish color. It's part blue from the blue laser excitation, part red because the sample is luminescing. It's this diradical in polystyrene. And what Rispano is going to do is to bring up a fridge magnet in a glass vial, And I need to get it to play in time. Oh, there we go. Right, okay. So there comes the friction magnet. If you look at the screen, there is the change in the luminescence. It is quite eerie because the amount of magnetic field is a couple of millitesla, and you can see what's it's trivial. I mean, I have to do it now, but there is the magnetic field change in the luminescence. It's a long way from a solar cell, and we never intended to get here, but it's turned out that that's where our journey has taken us. In principle, this is quite useful as a fluorescent label in fluorescence confocal microscopy in the life sciences world. If you can modulate a luminescent signal, you can detect it against the background, whereas if you've got not much of it, you can't tell that it's in the background. If you can wobble it, you can see it quite easily. At least that's the proposition. So that is my last slide. I should acknowledge some funders. The great thing, I don't want to brag, but the UK made a very foolish decision to leave the European Union, which is damaging on every front. But we have been allowed back into the SNAPS funding programs, and the European Research Council is wonderful, and it's allowed me to get this work going. And I have some other funders who've been very helpful, Simon Foundation in the US included. So I hope my journey hasn't been too chaotic. If I could take you back on two themes. First of all, if something is bright, it's really interesting. You can do things with it. If it's dull, it's dull. The second is, whenever you work with molecules, you're probably going to have to do something with the spins. Most of the time, they're a nuisance. Just occasionally, we can control them and get very surprising and useful effects, which have allowed very good engineering of OLEDs and maybe into other applications. Thank you very much.